So Keith had asked me to talk about today is, sort of where we're going with the next system, and as we design the leadership class computing facility. So I want to spend most of the talk on that, but just a little recap on who we are and what we do. I think most of you know TACC. We have a lot of computers. They're kind of large. In our current incarnation, we operate a lot of machines for the National Science Foundation with a lot of different missions across those different machines. Frontera is our big sort of capability system. It's 500,000 cores, thereabouts, 40 petaflops. Stampede 2 is more the capability platform in scientific computing. So we have about 50 project teams who have access to Frontera. We have 2,300 project teams that have access to Stampede. So even though it's one's 6,000 nodes, one's 8,000 nodes, but the fraction you get is a lot smaller on one of them. Jetstream is more of a containerized cloud solution. Chameleon is more of a CS testbed where users get root, and there's a variety of architectures. So we really have a host of systems that we operate for NSF that hopefully will be consolidating at least the funding streams under one banner. Getting those platforms under one banner is another matter. So, as well as some machines that we do for just our Texas audience here and our industrial partners. We just added the graphics to the new Lone Star 6 yesterday, thanks to AMD and Dell, who are in the room, who paid for the banner that we put on it. That's the GRC immersion tanks that we have there. And so those are, I think, in those tanks that you see, which before were just a plain white with a lid, so we called them the space coffins. But now that they have the attractive wrap, there's 336 servers in there. At 128 cores apiece. It's the high-end SKUs for power, so it works out to, you take 42U of the space, there's 4 of those tanks in there. They're about 70 kilowatts a cabinet that we're successfully cooling, including having the InfiniBand talk to them and all that kind of good stuff. So, so that's the newest machine that just went into production in the last 2 months. But collectively, we have about 20,000 machines. We have over 1 million cores. We have 1,000 GPUs. We deliver about 7 billion core hours a year to our user community. And we support really the entire open science academic community, right? We have users at about 400 different universities. This is some of the covers that our users got last year. In fact, the computing and science engineering issue was just a whole issue of stuff that happened on Frontera. But we got a few covers of science for one of those is pre-tornadic thunderstorm formation. One is water transport through various kinds of membranes, I think looking at desalination applications. But generally, if it's unclassified and it's open science and it's at an academic institution, we probably support it at this point. A few of our favorite projects, I just pulled from the 2021 highlights on Frontera, but a lot of earthquake, that's our big set of seismic codes, is multi-fault, multi-rupture earthquakes a lot lately. Looking at new methods there. This is one of the big ones. As John mentioned this morning, most of these users can get to pretty large scale. Although this one's more of a throughput problem. We deal with a lot of the big instruments that NSF funds through the large facilities program. So IceCube is that 1 cubic kilometer block of ice they've converted into a neutrino observatory. And it's yet another one, much like the work we did with LIGO a few years ago, where the forecast of what would happen in the experiment was decades ahead of us actually building the experimental apparatus. So last March, they announced their detection of glacial resonance, which was forecast as an indicator of antineutrinos being produced. That was forecast in 1960. It's amazing how collectively stupid we can be as a species and still have people who can do things like this, where 65 years in advance they could say, we would one day be able to build an instrument to detect this phenomena that they predicted. If you ask me to predict something about computing in 65 years, I'm probably not your person. So, but nonetheless, so that was a big Ensemble Monte Carlo thing. This was a fairly cool one with a researcher at Connecticut, where they went from the sort of little balls they use to sort of deliver nanomedicines, right? In this case, delivering chemotherapy drugs, obviously highly toxic. You really want them to get to the tumor, and the idea is to kill the tumor before it kills the rest of you. So you'd like them to just go to the tumor, ideally, right, and not spread around. And they found that this sort of nanoworm, the little wiggly guys you see in silver in the image there, is a better shape for a couple of reasons. One, it can sort of wiggle through the red blood cells and get around 2 of them stuck at a corner to turn, and they're also magnetic. So you can use a magnetic field to guide them to the tumor once they've been injected, and you get a much higher percentage of the medicine delivered directly to the tumor as opposed to the rest of you where you would like to not have it. So this, as our previous couple of talks, if you were in this room, but for the keynote and then the last talk of the other series, were a lot of these workflows that start to combine AI with more traditional scientific computing. One thing that we've observed that I think the last keynote speaker also called out is that the time to actually generate the data often exceeds the training and inference time substantially, which makes you think about what your computational makeup should be there. But this is some work with the Flatiron Institute and Carnegie Mellon, Tiziana DiMatteo, who's been a long-time user, but essentially taking images of regions of the galaxy and training the network between high-res and low-res images, and then running your sort of full universe simulation on the low-res and letting the neural net upscale the image for you. Got published in the Proceedings of the National Academy, 500 times the computational efficiency. Still takes the whole damn machine. So another one in a similar vein, AI that is not deep learning. I try and find some things that are not just neural nets in the AI space, but this is a support vector machine work in materials design, looking at a number of parameters in the production of photovoltaic materials, not just the material, but the temperature of annealing, the number of annealing steps, things like that. And they've produced, both produce better materials and reduce the computational requirements. So we really have this sort of wide range of science problems and also at a wide range of scales. And it turns out part of this is the success of the center, because this is a little faster than Moore's law, but to this morning's topic of, will you ever need exascale? I would point out that when we were at the, y=0 line there at the beginning of the center, we had requests for about 5 times the computation we produce. We have, 80,000 times that much computing available now, and we get about 5 times the requests for the amount of time that we can produce. So apparently demand for computing is invariant and not in any way dependent on the size of the computer you buy. So, so obviously you should buy a bigger one. There's some holes in that logic. You can work your way through it. But but as long as the program officers don't figure that out, we'll be okay. So, so anyway, so we've obviously seen this ridiculous increase in scale. We've seen ridiculous changes in hardware and hardware capability over time. The software changes are equally amazing. And the range of problems that we see is getting to be equally amazing. So to get closer to the topic that Keith actually asked me to talk about, I think it's fairly likely that in the future, we'll see a lot of things happening in federal funding that will recognize the diversity of applications for HPC, high performance computing in general, hopefully not in such a way that it diminishes the core funding for high performance computing, which is always the danger of adding more programs around these things. But as Andrew talked about this morning, the exascale computing project is humming along, and we'll wrap up in 2023, hypothetically. I'm sure they'll find a way to make it take a little longer, and then they'll find more funding after that to keep some of those things going. But that will technically complete in a couple of years, and there's several things floating around OSTP, the Office of Science and Technology Policy at the moment, that are potentially new streams of funding for large-scale computing, at least 3 of which I'm at least peripherally involved in. One is the National Strategic Computing Reserve, or the NSCR, which looks at sort of the wave of computing we were able to mobilize very quickly around the COVID pandemic. A lot of us in the federal computing space found ways to turn that into extra funding at some point, but also into a lot of impact. And we've gone back and sort of pointed out that that none of the success there really happened by accident. It happened because, for instance, in the vaccine development, and that we had people who put their whole careers into molecular dynamics and viral structure and propagation, and those users knew about our computers and they knew our tools, and we had a lot of data in place, fortunately, from SARS and HIV to put those pipelines in place. But not every disaster do we have that level of preparation. And big computing matters, and sometimes the time to get things done matters a lot. So there's a fairly strong lobbying push and white papers floating around about the structure of that would allow us to create not only systems, but the sort of training and exercises and data and software tools that we need to be ready for future, whether it's pandemic or chemical spill or rampant wildfires or, I don't know, collapse of the Texas power grid or other unthinkable things could happen. So the second one, and I'm on the task force for this as well, is the AI research resource, which looks to be a fairly large coming investment, maybe spread across a few of the agencies, DOE and NSF among them, in creating resources for people doing research in AI. This has Congress's attention. What mostly has their attention is that most of the papers at this point don't come from the United States. So, so potentially some sort of catch-up in capability there. And there's an interim report going to Congress and the President in May, and a final report just after the election, which is the worst possible time to do it. So nothing should happen in the next couple of years. But hypothetically, that will be moving along in the sort of fiscal 23, fiscal 24 timeframe. So, and then in the NSF space, and this is the thing that is sort of tax future at the moment, that I'm the PI for, is the Leadership Class Computing Facility, which is about sort of coming up with a more sustainable way to invest in computing than one-off system competitions every 4 years. If you're an Exceed user, the thing about Exceed ending actually went out this morning, and you got an email that said, hey, everything's going away in August, but there'll probably be something else coming. So it's not announced yet, but it'll be fine, was the gist of the email. But in particular, I want to talk about the LCCF, because that's the thing I've been deeply involved in planning lately. So, and I'm going to give it a better name and a better logo before it's over, but that comes later in the funding cycle. So, but the basic elements of this are to replace our current Frontera system, which, believe it or not, I think John said 2 years, but it'll be 3 years in June that that system's been up. So as an HPC system goes, it's still, I believe, ranked 12th on the top 500 list, but it's getting old very quickly. So we need a follow-on, and the only written instructions are 10x faster. And we've had, I can't tell you how many hours of conversations over what 10x actually means in that context. So is that application throughput? Is it peak application performance? Does it have anything to do with flops? I've argued no, although that's going to fall out as about that anyway. But we also want to look at a more, perhaps DOE-like, but a more holistic long-term view of how we support the sort of largest applications in the space, and to be an anchor of the NSF computing environment in the way that NCAR is for atmospheric research. And to deal with all those different use cases, and I think I have one from each of Steve's 4 quadrants from this morning, that we somehow have to cover, and convincing people to not use the exact same hardware for all of those problems. But, and then of course, workforce development is a big piece. And robust public outreach means convince Congress they're happy enough to not take away your funding. So, the question then becomes, how do we get from the Frontera system we deployed, which is technically phase 1 of the LCCF in 2019, to actually deploying Horizon, which should go into production sometime around 2025, if DOE doesn't steal that name and I don't have to change it again when they put out a system, or NASA or somebody else. So in a nutshell, and this ignores, there's a book about this thick that's called the Major Facilities Guide, which leads the rules for accounting that we have to do. I've, in our last preliminary design, and Andrew's had to do a bunch of these similar reviews, but I think our packet that we submitted to the NSF was 3,836 pages long, and I've tried to bring none of those pages to this presentation because I think there's a danger of, well, it might cure insomnia, but it could be fatal to read them all. So, I've never seen how thick they are printed out, and I never want to. But there's a terrifying amount of project management that goes into these things, as anyone who's run a large government project can tell you. But in a nutshell, what we really have to do is figure out the requirements, evaluate the technologies we can use, because we're not, as I said this morning on the panel, we're not really in a position to make NRE type investments with the vendors, to customize the technology, and then we need to evaluate the applications that actually need to run on the machine and figure out how to get them there by 2025, where we have stolen many ideas from the applications part of ECP and the way that Los Alamos procures machines that were talked about earlier today. So the requirements process is the one that review panels want to hear about the most, and you probably want to hear about the least, but the normal way to do this is to hold lots and lots of meetings and let people talk till they're blue in the face about it. That's fun the first 6 to 9 times, and then diminishing returns after that to run 1,000 workshops about computation. But it turns out there have been 1,000 workshops about computation, so we tried to say, look, we're not the first people to think computing is a good idea for science, so let's steal from the many other places that have. So we did some direct gathering of requirements from stakeholders. We did a lot of mining of our actual workloads to figure out what is the gap between the PowerPoint version of what people say they run and what they actually run on the systems, which turns out to be substantial most of the time. And then looking at the vast number of reports that are out there in the community. So, there's a National Academies level report about every 2 years that computing is important. So we used a lot of those. We used a lot of these sort of, you can pick a field of science and search for a report that says grand challenges. And I guarantee you, if you read said report, computing, data, or AI will come up at least 150 times in the context of that report. That is not speculation. That might be something I spent way too much time doing. So, but whether you're looking at mapping the human brain or where to place wind turbines or, virtually everything in between, you can find a workshop report that says there's a lot of computational challenges out there. It's a little less settled in the AI literature, but there again are a million great reports. The DOE AI town halls and the DOE scientific ML report are among the best. That also points out that we could just build machines for AI and that would swamp our workloads too and be more computing than we could handle. So there's a lot out there, but just to sort of summarize what we saw in a very short nutshell, and there's a lot more to this, but and I think many of the talks we've seen today were great examples of this, especially in the application sections, but the models are more complex, right? So they're obviously bigger, but more multi-physics, more multi-scale, more multi-rate. I have a couple of examples, and we can see a 10 to 100 increase in scale just from the models themselves. We see moving from sort of Ford simulation, solve a problem once, to these outer loop problems I alluded to this morning, uncertainty quantification, inverse problems, data assimilation, optimal design, optimal control, simulation-based decision making. So, you can do 100 to 1,000x scale up on the amount of computation you need for that. And then obviously the role of machine learning in all of this, which while hypothetically reduces the amount of computing you can do, seems to drive us to do more and more. We can apply it in more and more areas. So, and then of course we're doing this, as you all know, in an era where computer architectures are getting more complicated, more concurrency, more heterogeneity, and programming models are also changing. As Andrew said this morning, there's so many new tools out there at so many different levels of abstraction coming along the way that we really need to coordinate the sort of architecture, algorithm, and application space. So, that's sort of what we saw in needs. Typical things, and again, the last keynote was a great example of this, but this is a workflow we see: seismic risk assessment for gas pipelines, and it again is AI infused, and these are just sort of ANSYS simulations to get the training data. But in this particular case, it was 200,000 runs, each of which generated about 10 gigabytes of data. I think they've since done 1 million runs. This is a group at UCLA who was doing this. So, you generate several petabytes of data through hundreds of thousands of Ford simulation runs. So being able to simulate the geometry of the pipe, it's great that you can do that. Now go do it a few 100,000 times, right? So, and then that data gets reduced to strain curves, which take your 2 petabytes and reduce it to a few hundred gigabytes. And then from that, you train a neural net and you build the strain models, and you have this 12 megabyte model that you can actually, practically use and hand around, do inferences about, in this kind of soil with this kind of turn, is this pipe, a reasonable geometry. So, but there's a lot of different codes there, right? You have your data reduction step, you have your Ford simulation step, you have your machine learning steps, and again, the Ford simulation tends to dominate the computational piece, generating all that training data, or generating the inputs that get reduced into the training data in this particular case. And we're seeing that pattern over and over again. We're also seeing a lot of drivers for interactivity, right? So this is a problem that ends up running some fairly large computation for resonant frequency of a particular building site, but it starts out as a Jupyter notebook, right? So you're starting with essentially a graphical user interface. It's in Python. People want to interact with it. This is not our traditional workload, right? So, but there's more and more of that around that we see. So we need to support not only our 500,000 core simulations, but somebody moving widgets in a Python notebook has to generate computation somewhere. So this is as close as I will get to the giant requirements table that was in the 3,836 pages. I'm never going to forget that number, by the way. So the that were in the packet of sort of what we translated are sort of million data points of what people want and what problems want into really 5 science requirements, right? These are our foundation requirements, right? That we need that at a minimum we need 10 times bigger or 10 times a more capable system. You can certainly argue for more. We'll run out of money, but it needs to cover a broad set of science and engineering use cases for us. That we need to support the full life cycle of a computational analysis, which might be from data acquisition to sort of publication of data sets at the far end and putting out DOIs and long-term thinking about data life cycle. That we can, I say stable programming model. That doesn't mean it doesn't change, but you have to make a long-term sustained investment to incent a gradual change. And again, ECP has been a great example, but you note the numbers there, right? 24 problems, 78 codes, $1.8 billion, right? So do the math on the per code spend you have to do to move programming models effectively. So in our case, we're spending a lot less per code by, I don't know, just move the decimal over about 5 places. So we need to basically make incremental change, right, to get users to follow us anywhere we want to go on this. Obviously, machine learning methods and scientific computing at scale and these emerging workloads are going to be a key piece. And then we need to have a workforce that's capable of doing something about it or we're screwed, right? So where we can build a machine that is so wonderfully complicated and brilliantly designed that no one can actually use it, right? So that's the thing we try and avoid. And so we translate those into technical requirements through an arcane process, which I would hope to never explain again, but there is one more design review. So, somehow I turned that into 15 megawatts of power. But we're going to add 15 megawatts to our capacity. That's in addition to the 10 we have. So really, we'll be up to 25 megawatts. And we have various things in terms of the technical things that we need to do to actually achieve those science requirements. So, so that's sort of talking to the community. What do they need, right? The next thing is, all right, can we actually build anything that they need? And so without telling them their roadmaps are completely wrong, you need to tell them they're just a little wrong and they need to adjust for us within the boundaries of the amount of wrong they're willing to accept. And so we've done a huge number of on-site evaluations. We've done others with partners and I think I hit most of the companies that are exhibiting down there, and they're all grateful that they're on the slide, but the few that I've missed are undoubtedly going to complain in the next 20 or 30 minutes. So things to look forward to, but we've looked at a wide variety of processor technologies. I mean, for AMD, Intel, NVIDIA, this is CPU and GPU evaluations, right? We've looked at various and sundry ARMs. We've looked at next silicon, just in the sort of general processing. We've looked at a bunch of networking options, right? Cornelis, OPA, Mellanox, InfiniBand, now NVIDIA, Rockport, the switchless optical, sort of Ethernet physicals, but on a 12D hypercube without switches and just all optical shuffles. We've looked at file system options. We actually switched Lone Star from Lustre to BGFS, because that's sort of a modest scale system with just about 600 nodes, 60,000 cores, so we could start building some experience with a non-Lustre in production or GPFS. So still looking at can object stores actually work in our space, doing a lot of DAOS testing lately. We've bought switches from the node disaggregation vendors, both of which are in the process of coming up at the moment, but Giga.io and Liquid. And then we've looked at a lot of the other more exotic things with partner sites. For instance, with Cerebus, GraphCore, Sambanova, Argonne buys all these chips, so I just call Rick Stevens and say, how's it going, rather than trying to emulate what they're doing on that. So, but really a huge number of technologies where we can start to map those science requirements into what we can actually do. And again, if you take those requirements and start translating them into what we should have, right? So for instance, one of them was we really want to look at the full life cycle. We need the capability system, and we also need an interactive system, and we also need something that supports always-on services, right? It can be there 24 hours a day, so when you're doing a capability run, those services can't just turn off, right? So, so what we came up with is that we will define the size of the system, and then I will lie about it because we'll buy more than that. And by the way, if you'd like to know how the government works, I was very expressed about, we're going to have this piece of the system that does the 10x piece, and then we're going to have a bunch of additional racks to deal with all these other use cases that don't count towards the capability, so no one should ever run across them. And on Monday, I got the question from an unnamed program officer, what is the peak flops of the entire system if you include all those pieces? And I'm like, that's the question you weren't supposed to ever ask. So, and now I have to make up an answer because no one knows what the peak flops of 2025 are on any of these processors, let alone the achievable ones. So I wrote an answer and sent it back. So, but anyway, so we'll buy 100% of the system, and then we'll buy 10% more than that to deal with some of these other use cases. So we'll have 110% of the system, so when someone wants to run on 100%, I still have a bunch of racks doing other stuff, like managing Jupyter notebooks and services and things like that. So, or doing interactive hyperparameter tuning for somebody's big machine learning model. So, and we'll have some distributed systems around too before I get into the data side. Let me say that 10x in that time frame is challenging for a couple of reasons. One, if we look at the Frontera baseline, if we just did nothing but relied on vendor performance improvement in the same line, Frontera is mostly a CPU-based system, right? We think at best over this sort of 5-year time frame, maybe we'll get 3x out of that. And most of that we think is coming from the additional memory bandwidth. We're going to see both DDR next generations go into much higher clock rates than we were expecting and more channels, but also the sort of prevalence of HBM everywhere will really change the memory bandwidth we'll have available. So, but 3 is not 10, so that's 3x. We went with the old-fashioned solution to get the next factor of 2, which is buy more. That one almost always works, especially if your problems scale. Sometimes they don't. We'll get into that too in the next 6 or 7 minutes. So, so we're going to double the budget over what Frontera was, and I got away with that. So, so that'll get us to about 6x, and we think the other, so you need another 50% or so, right? You get from 6x to 10x. So the remaining factor of 1.5, 1.7 is going to be improvements in software algorithms and methods, right? So, whether it's use of a surrogate model, like the last talk showed, or just tuning the code, there's so many, or tuning the I/O. We still have the standard, this checkpoint was 12 hours on my laptop, and now I'm running it at 80,000 cores, and the checkpoint interval is 34 seconds. And the code just does I/O over and over again until the metadata server collapses. So, happens all the time. We have a term called Tommy jail for what he does to them when users do something like that. So, where if you're coming to the system management workshop on Thursday where Tommy's speaking, yes, you get put into Tommy jail when you do that, and you have to convince him by making a certain kind of sacrifice that you're not going to do it again in order to get out of Tommy jail and run some more. And there is a number of IOPS that get you there. So, but nonetheless, we actually want to make some software improvements, and everybody has said repeatedly, and not only for this reason, but I regularly hear that you're crazy when I say we're going to make software improvements, and then I started actually measuring the code. So a couple slides, I'll show you, why I think we can actually do that, with maybe a less intensive effort than Andrew's team has to put into improving codes. Rewriting from scratch. So we're also going to make some changes to the way we do data systems. Something we experimented with Frontera is we went from having 1 scratch file system to 4 scratch file systems, which means when you get the pathological user, and I don't know what they run, but it feels like while one fork open is their basic code, and they read like 4 bytes. But at this point they can crash at most one of the 4 scratch file systems when they do that instead of the only one you have. And so that's been actually really good for uptime. And the things that are not in the user guide is we really have this sort of default scratch file system, the people who do really big I/O scratch file system, the problem child scratch file system, and then the flash one for the people who can actually effectively use really fast storage. But we have one more old problem children go. So, and I'm not going to tell you which ones, because that might tell you when you get an account where we think you belong. So, as we call them, scratch 1, 2, 3, and 4. But that's been a pretty good model, but I think what we've learned over time is that our sort of one giant scratch file system for all problems on the system model, especially in our environment where there's a lot of multi-user, certainly a lot of people have data parked on the scratch file system at any given time, that trying to scale to meet all needs in a single file system is painful and probably unachievable in the near term. So we're going to have differently tuned volumes of different kinds of storage there. You know, the cloud solution to this is don't do it, right? You have the no persistent file system model, and everything is dynamic and has to be migrated in from the object store into your temporary scratch file system, which adds a ton of overhead. I think both those models are broken, right? So we're thinking we might do as many as 30 independent volumes that would be sort of on a per campaign basis for project teams that they could park on like Scratch with a sort of bigger second tier Scratch. We already have this called Work. That's a sort of a longer term Scratch. So as a second tier, and probably those Scratch volumes will be presented because of the way a lot of the AI users would like to use them as either a shared file system or just direct attached block storage. Visible on the nodes as a local file system where we don't try and keep POSIX semantics across nodes for sharing and things like that. We actually see a ton of usage of just local temp space we put on disks now, so, or on compute nodes now. So, and then once you've made it off the second tier of Scratch, you'll go to one of two places. One is the more traditional archive space, what we've called Ranch is our archive. That will go there, and the other is the publication space, right? The high integrity space where the data is actually available online. You go through, put in some metadata, publication pipeline, and you end up with a DOI for your data set, and people can go get it, right? And that's our publication or collection space, which will evolve from our current corral. So that'll be sort of our 4 tiers of file system that we'll put in there. So, and then the last thing we have to do is, you know, from my 3 things we have to do, evaluate the applications and help them get there. So it turned out as we were doing this, we had various and sundry benchmark suites from 2006 that NSF had used to buy systems. You know, we have micro benchmarks galore, and we have everybody showing, you know, that on this particular version of this application they can do great, but not necessarily that they can do real science with that. So, so we really had 3 problems. One, I have to convince various ranges of people what 10x means and that we actually did it. And one of those ranges of people is government auditors, right? So, so I need to have a straightforward definition that an accounting believes, and also one that a scientist thinks is 10 times better, and that the people funding us think we're doing cooler things, et cetera. Along that line, I need to actually articulate the science impacts of what this thing's gonna do. And we need to get our user community ready to do something useful when it happens. So we created this thing we called the Characteristic Science Applications Program, which is like the tiny little version of Andrew's ECP Applications Program, sort of try and simultaneously take a shot at all 3 of these problems. So, you know, on the science impacts, you know, I think, especially in this crowd, we know if we build a bigger machine, cool stuff's gonna happen. But I can't sell hundreds of millions of dollars of investment on cool stuff is gonna happen. And I don't have Stephen and Gary's problem of, well, we have this nuclear bomb and we don't know if it works or not anymore. And if you would like us to answer that question, we need a lot of money. So, so I need to come up with something else, right? To say that something good is going to happen with the system. So, and we know that many of the things that will happen are not things we can forecast. That's why it's called discovery science in the first place, right? But the bigger and more argument just isn't going to sell this, right? So I need a specific set of things I can say, well, if we build this, we'll be able to look at this problem at this resolution that we can't do now, and that's likely to lead to this kind of insight, right? So, or not, because it's an experiment, but you can't say that last part. So, and actually expect someone to give you money, because you can only do experiments that are successful in the government funding world. So that's why we call them experiments. Again, you just don't get wrapped up in the logic of this stuff. Yeah, it's painful. So, so we have to validate the capability, right? Convince everyone that we've succeeded. And we have to prepare the user capability for, the user community for capabilities that, hopefully will be somewhat new, right? And not just exactly the same as the old system. And as has been mentioned, every time you go up in order of magnitude and scale, you're going to break a bunch of stuff, right? I mean, that's just inevitable. In the software side and the hardware side, everything else, right? For some reason, the BIOS won't work when you have 10 times as many nodes. I've never figured out why that's true, but it seems to universally be true. So Murphy's Law is the most powerful of them all. So, and really, when you build these systems, as we've all experienced, right, the hardware is not long lasting, right? In 5 years, they're old, no matter what, right? So no matter how much you spend, no matter how cool it is when you start, you have sort of 2 years where you're cutting edge, and then you start, getting supplanted by newer and cooler things. And at the end of 5 years, I mean, just for power efficiency reasons, you probably want to turn it off. So maybe 6 years. Building the system and then having the users show up and figure out how to use it when you have that kind of time frame is a horrible idea and a horrible investment. So we wanted to come up with a way to effectively engage with the science community, and I actually talked NSF out of some money for this. Except instead of spending 1.8 billion divided by 78 codes, 20-ish million dollars per code, we're going to do it on $150,000 per code per year. So, but nonetheless, we went through a solicitation last spring in early 2021, looking for sort of the right kind of problems, right, as ECP did as well. But we just threw out a broad call for proposals, looking at, propose your problem to us, not your code. First, just propose your science problem that you want to solve. Tell us why it's a significant problem. Tell us why it's representative of other computing problems that will be out there. Tell us why it's suitable for a big machine. And we actually, I thought we'd get 40 or 50 proposals. We got 140 good proposals, and even after you threw out the crazy ones, there were more than 100 good ones, which created its own sort of problem. So we took about 30 of the best of those across the portfolio and looked at, over the spring and summer, sort of getting into those codes and validating the assumptions, right? When they say they can run on 1 million nodes, is that like, I don't know, true? And it turns out, in 2/3 of the instances, it actually is true. So, and in 1/3 of the instances, perhaps it's not. So, but we selected 21 projects to go forward, and then we went through the excruciatingly long NSF process. And just recently, at the end of January, they got through the review process, and we're good to go, starting on actually funding someone on the project team, the science side team, for the next 2 years to work with us to get the code ready and to establish the figure of merit, do the baselining against the current system and the things that we need to do, but also to explore how to make those better. So we're funding staff on our team and at the application team to look at these codes. And the funding people at the application team is really the new part that NSF has never really done, and DOE's done a much better job of than we have in our space. So, so we've started these 21 projects in the 2 years until we actually start construction. Some of them will continue during construction for another 2 years until we get the system into full production. So, but it's sort of the one postdoc level for each of these places. So, and this is just a few of the profiles that show you the great range of codes and why we think there's a lot of evidence that we can improve things from how they typically run without necessarily recoding the whole thing. But, and again, I'm holding back the names of the particular codes to protect the guilty here, but we just did some roofline plots really quickly. And if you haven't looked at this kind of plot, so the x-axis here is the sort of flops per byte, so that's the data intensity, and that y equals x line, the 45 degrees, is when you hit the memory wall, right? So you're limited by memory bandwidth if you're on against that diagonal line there. And then these are for CPU nodes. We also did some on GPU nodes, but then you have gigaflops per node on your y-axis here. And then the data points are running this particular code in this particular data set in that particular code at the number of nodes by the blue dot there, right? So, and results, as you imagine, are all over the map. So here's a pretty good code. It's an electronic structure code. I'm not going to give away the name. That is a good code, but it has pretty poor, strong scaling. And by the way, the various vertical lines for an Intel chip, that the bottom line there is the peak scalar performance, right? So if you just no vectorization at all, right? Your peak scalar, if you just used SSE instructions, right? The original vectors, that would be your peak performance. If you use all AVX2 instructions, that would be your peak performance. And if you used all the AVX 512 instructions, that would be your peak performance. So there's no way to get above that line. In fact, if you ran all AVX 512 instructions, the clock rate would slow down enough you can't get near that line. But still, it gives you some idea of where and sort of the capability of the processor you're hitting. And you see at 50 nodes, this code does pretty well, but they really don't have a big enough problem to do strong scaling here. So, because by 2,000 nodes, they're doing much, much worse, right? So, but that's a pretty good code, and that peak number for 50 and 400 nodes is actually really good to get above the AVX2 one. That's sort of ridiculously good for any production code. This is a seismic code. It's the best of the earthquake codes. And there you see it's 1,000, 2,000, 4,000, and 8,000 nodes, and all the dots are on top of each other, and they're way above the SSE line, right? That's like 40% peak performance at 8,000 nodes. So for that to not be LinPack is impressive, right? That it's a real application doing something. So here's a well-engineered, really good code. And if all the codes were well-engineered and really good, I'd worry a lot about our ability to make improvements and hit the numbers. All codes are not really good, well-clustered, well-engineered codes. Most of them are what we call software. And so, so this particular code uses the famous C++ template libraries. And the first graph here, you don't actually see any dots because they're all clustered at the origin. With, let's just call that 0 performance on that particular code. So we blew it way in where the scalar line is now the top of the graph on this one. And you can see that you still get almost nothing. You're neither memory bandwidth bound nor compute bound. And your scaling really starts to fall off after 2 nodes. So it heads for the x-axis. So, and they're like, oh, we can run at 1,000 nodes. And we're like, yeah, if you want to do like 1 floating point operation on them every 2 days. So, and that was sort of a one-off, fairly boutique code for a particular group. So, there's some slack there. The last one there is a widely used community code in cosmology, astrophysics. And it's nowhere near the memory bandwidth limited, but it's also not limited by anything in compute, but it is well clustered near 0 for different problem sizes. So that's exciting, but my guess is we can make that code a little better without doing too much to it. Probably, I don't know, fetch a K of data at a time instead of 4 bytes or whatever they're doing from storage. So, so this is sort of preliminary scaling, but it shows that there's a lot of work we can do to actually make these things better. And none of this really has anything to do with the architecture, right? It's just, is the code any good or not, right? And that's sort of the place to start on some of these things. So, so we did, we actually had some places where there were way too many good proposals in a field, and we wanted to have a good representative portfolio. So we split it up a little bit, and I am really about to stop, Keith, I promise. We tried to pick the good science first and let the architecture fall out of that, right? Turns out good 60% of them are nice GPU codes at this point, so that gives us some more range to work with. And we tried not to limit ourselves to single codes, but look for the whole end-to-end workflow to get a real science problem. And we are doing some weighting in the figure merit formula by historical workloads, right? We know there's going to be a lot of cosmology. We know there's going to be a lot of molecular dynamics. So we wanted to weight those a little heavily, but we ended up with 21 that we selected. I won't get into the specific names, but 8 of them are from sort of math and physical sciences. We just had so many good astro proposals, but we picked 4 across sort of different areas of the field, whole galaxy simulation, stellar combustion, that kind of thing. 3 that are more or less materials. One of those is materials with deep learning. One's more of a lattice QCD problem, which is also arguably materials. How stuff in the physical universe is a big topic. So there's 3 from engineering, hypersonics, turbulence with an AI component. There's 6 from the geosciences of particular interest here. But a lot of those are more climate. There's a tornado one, a climate modeling one, an ice sheet model, and then sort of 3 different earthquake-related ones from fundamental mechanisms to plate tectonics driving earthquakes to earthquake damage assessment. 3 in the life sciences area, viral infection, aerosols, the MD plus AI protein structure that John mentioned this morning. And then 1 that's sort of somewhere between computer sciences and social sciences that's deep learning for misinformation detection, sort of a pure AI problem. And so these are what's going to drive, is the system good enough, right? Not the number of flops. And can we actually make improvements? But again, we're going to spend about $300,000 on each code and see where we can get. So But that's where we're going with that in terms of picking our machine. And you probably all wanted me to say, what machine are we picking? And I'm not going to, because honestly, I haven't made a final decision, because the best way to be wrong is to tell people 4 years in advance what your computer is going to look like and what it's going to do. So I always stop that at 2 years, right? So 2 years before we deploy it, ask me what it's going to be. But we actually start construction, fitting out a data center. It'll be 2 years from today, should Congress pass a budget in something resembling a timely fashion in FY24. So you can hold your breath or not. But but notice we did pick March 1st, not October 1st, because we're just assuming they'd be 5 months late. So, but yes, hypothetically, we start construction March 1st of 2024, hoping for system deployment in the first half of 25, and science users on in the second half of 25. And then we will actually have a long-running investment where they promised us operations and maybe an upgrade in there, 2026 to 2036. So, you know, so we've never had more than 4 years of funding on an NSF system before as the initial commitment. You know, Stampede, we had a renewal option. Technically, there's a rule that, you know, no NSF grant can be longer than 5 years and can only have one renewal and can't be longer than 10 years. But the reason I say we wanted to build an in-car-like facility is it's been sitting there funded in Colorado since 1957. So perhaps my real challenge is figuring out personally how I was going to get around that limit that technically exists. So, but if NSF approves, the Office of Management and Budget approves, Congress approves, and they pass an FY24 budget within 5 months of being on time for the FY24 budget, that's the plan. Let me thank all the people who do this, because again, you know, the computers are easy, the people are hard. So it's a team of folks that makes all this happen, and I just get to talk about it. So with that, I will stop. So take questions. And I think when the questions stop, you can start drinking or something, right, Keith? So, you know, just keep that in mind. Way over there, Keith. There's one coming that way.
10 years is a very long time for a large system to be in production. What risks have you identified associated with that, even with an upgrade potentially 60% of the way through? What concerns are still unknown, or known, I should say?
Oh, yes. We have known unknowns and unknown unknowns and an extensive risk register in that 3,000. Did I mention it was 3,836 pages that we put in for that? But, so upgrade means forklift in our particular situation, right? So there are an enormous number of risks. Keeping in mind our requirement to keep a fairly stable programming model for our community, the idea is basically we'd buy a second system, halfway through that life, right? So it's 2 5-year lifespans. We would like to avoid a radical change in architecture because that gives you a radical change in usability. If a path closes down and disappears and isn't there anymore, right, then we may have to force that upon the user community, and that is certainly in the risk register, as you might imagine. Yeah. Other questions? Just opportunities to tell me I'm wrong in public.
Everybody wants to have a drink?
Dan, thank you very, very much.
Yeah. Thank you so much.
Great talk and really
great to be here in person. That's so much more gratifying than the little icons on Zoom that say clap.